All right, well, for our concluding talk for this week, we'll finish up the lecture series with Isabel Garcia. So, Isabel, take it away.
Okay. Hopefully this is good now. Okay. Right, so we finished the last class building our way to just writing down sort of the free energy for a free scalar field. So we said there was a zero temperature piece and also a temperature dependent piece that is going to be kind of the focus of our attention. And this is with omega, we'll just think of it as the usual, again, dispersion relation for relativistic massive particle, and then sort of it's conventional to define this as some function j of b, and it will depend only on the ratio of the mass to the temperature. And then you can also show that a very similar expression exists for fermions with some different minus signs here and there. And all of this, again, we're just going to define. Okay, so this is where we finished earlier today. Yeah, so at low temperatures, I was just saying, below the mass of the particles, both of these functions are suppressed exponentially. So yeah, for very low temperatures, finite temperature corrections are just a tiny exponentially suppressed correction. At high temperatures, in particular, T much bigger than M, we can expand these functions. And so this is a little bit more interesting. So there's a constant term. There is a term that is quadratic in M squared. For bosons, and this is going to be important later on, there's also a non-analytic term that effectively is effectively kind of like cubic in the mass of the particle, and then there are further corrections of order m squared over t squared, and some can be logarithmic enhancement. And similarly, for fermions, we can expand this. We get something similar, except some factors. Crucially, there isn't a cubic term for fermions, so we're left with like additional corrections of order m squared over t squared, everything is squared. So we're interested in how particles that interact with some scalar field of interest affect its effective potential at finite temperature, right? So let's think. So we're interested in building the finite temperature potential for some field phi. Phi could be, one of the fields we were considering responsible for spontaneously breaking maybe a C2 symmetry or a U1 global symmetry. You could even think of this guy as standing for, you could think of phi squared as standing for like the mod Higgs square for the standard model. So the discussion is going to be sort of fairly general. So to lead in order, we can incorporate finite temperature effects in the effective potential. So this could be the zero temperature piece. And to lead in order in this high temperature expansion, let's say to order m squared over t squared, notice, so the contribution to the free energy is these functions multiplied times t to the fourth. I am going to ignore the constant piece because it doesn't change the equations of motion, as you know. So the leading contributions are going to be of the form, so for all the bosons that couple to this field, this is going to be t squared mb squared. And similarly, for all the fermions, this is going to be sum over t squared mf squared, and there will be additional contributions further suppressed at high temperatures. Now, this is interesting when, in many cases, like for example, in the case of the standard model, the masses of these particles depend on phi itself, okay? So we can think of these guys as a mass term that is actually phi dependent. And similarly for the fermions, this guy may be phi dependent, okay? So this is what gives us the leading order correction to the effective potential of our field of interest when the masses of other particles depend on the value of the field itself, okay? So notice that, so for instance, let me just start a new. Okay, so for example, if the masses of these particles, whether it's bosons or fermions, we can write them down as some coupling gi squared times phi squared, okay? Then I can sort of take all of these finite temperature contributions and write them as 1 onto some effective coupling that I'm going to define in a second times t squared phi squared, okay? And with this effective coupling as a sum over, you know, the relevant couplings for all the bosons and fermions of the theory. Okay, so so this allows me to write in particular. So continuing from the, actually, I'm just going to write it here. So this allows me to write in particular, so, okay, so let me write this again. So to lead in order, we're just writing this down. And let's say, you know, we can have in mind something along the lines of this is lambda on 4 for concreteness, something like this. So in particular, the term here that is quadratic in phi squared, now I can write down like this. So previously, so I can write it down as follows. So previously in the zero temperature theory, the phi squared term was just this piece, and it was negative, so the, you know, phi equals 0 is a maximum. Now I have this additional contribution at finite temperature, which for large enough temperature will be positive, okay? So, so I have some, now I can think of this as some kind of finite temperature mass for this object, and at finite temperature, our file field now fluctuates on length scales for their no longer, you know, the mass on the zero temperature vacuum, but the mass of these, the effective mass of this finite temperature vacuum. Okay. So this already tells you. So at very high temperatures, this phi squared term is going to become positive. So if we perhaps had some sort of like picture like this, or some equivalent thing, perhaps in the case where this is a U1, as you wish, at high enough temperatures, phi equals 0 is actually going to become a minimum, okay, with positive curvature. So this is basically the more sort of like refined way to see that symmetries are generally restored at finite temperature. So for example, so for the standard model, the approximate expression for this G effective coefficient will include contributions from the various bosons of the theory, so the Higgs itself. Also, the C boson with the 3 polarizations of a massive vector. 3 times 2 for W2, W minus, and then from the fermion sector, mainly from the top, 4 components for the direct fermions, 3 components for color. So it could be something like this, okay? So this guy would be a further the Yukawa coupling square, which is order 1. These guys here would be, further the gauge couplings of the standard model, and this would be a further lambda. One thing that is kind of obvious in this particular example is that this is bigger than 0, which is the reason why I was saying that for large enough temperature, the symmetry is restored. So phi equals 0 becomes a minimum. And that positivity of this sort of effective coefficient, that is true in general, but it's not like some sacrosanct principle that it has to be positive. And in fact, and I'm going to mention this kind of as an aside, sort of like there can be freak cases where this is actually not the case. So this is true in general, but there can be exceptions, and there are examples of these. For instance, so in the context of condensed matter, there is some weird system type of crystal called Rochelle shoals, some of you may be familiar with, that has, where this thing is basically like inverted. There's a system where like you actually lose symmetry at higher temperatures, and then you recover symmetry sort of like at low temperatures. And there is also a more kind of field theoretic example by Weinberg in a theory with like a number of scalar fields, written in '74, where he cooks up the sort of a particle physics model where a similar thing happens, where like the high temperature theory has actually less symmetry than the 0 temperature theory. So there can be crazy things that happen, just so you know. And this phenomenon goes by the name of symmetry non-restoration at high temperature. Okay, but in general, it's certainly not generic. It's a little bit sort of like a freak situation. Okay, so we see that it's sort of generic to have symmetries be restored at high temperatures. We do expect that our universe was an equilibrium thermal state in the early universe. We know from the CMB that the CMB is, to a very high accuracy, a black body spectrum. So at least at the moment of last scattering, the universe was in thermal equilibrium. So extrapolating back to further energies, we do expect that our universe was a thermal state, certainly, all the way up to the QCD scale and potentially beyond the electroweak scale. Okay, so that sort of forces us to confront, what is that happens in our own universe as we go from, very high temperatures where all the various symmetries were restored through various phase transitions up to now. And one of the things that can happen that I'm going to discuss now is the formation of topological defects. So the defects that we've been discussing so far, like domain walls, cosmic strings, also monopoles in more general theories. These things can only exist after a spontaneous symmetry breaking, okay? So if you try to think about how could these things be produced in the real universe, they only exist after a spontaneous symmetry breaking. So notice that already looking here, the temperature at which that mass square goes from being positive to negative, typically that's going to happen at what goes by the name of critical temperature, and it's going to be of order the scale of spontaneous symmetry breaking, okay, as you might expect. So defects only exist at temperatures that are going to be sort of like below this temperature, and then you can ask the question of, so typically, you can ask the question of like, okay, what would it take for me to produce cosmic strings or domain walls from the collision of individual particles? So production of particles that are much heavier than the relevant temperature of the plasma are always suppressed by the corresponding Boltzmann factor, okay? And I told you earlier that these types of defects, in fact, become more and more massive as the theory becomes more weakly coupled. So these things, so the mass of these objects, as we saw earlier, is always typically some power of, well, it's always something like the scale of a spontaneous symmetry breaking divided by some coupling to some relevant power. Okay, so these guys are always in the regime where their production through processes like particle production are incredibly exponentially suppressed. Okay, so this is not going to do it. Something else needs to happen, and that's where the phase transition plays a very important role. So let me explain that. Okay. So yeah, production of these types of solitons or defects requires a phase transition. So here the crucial observation is that, so I told you here that at finite temperature, the field phi will fluctuate on length scales for the inverse quantum wavelength, okay? And that will, to some extent, set the correlation length of the field, okay? The field will only be correlated on distances roughly of that order. So in some sense, as the phase transition happens, the vacuum that is chosen by the Higgs field will be uncorrelated at distances beyond the correlation length of the phase transition, okay? That can differ depending on whether the transition is first order, second order, but there will be typically a final length over which the value of the field is correlated, okay? So in a theory where there are various vacua that are degenerate, whether the Higgs chooses to be in one or the other, will be a choice that will be made sort of like independently in different regions of space that belong in different correlation volumes, okay? And then the observation follows, and this was the insight by Kibble and also later on Surek. So this goes by the name of the Kibble mechanism. And it's basically just the observation that in any phase transition, and in particular in a cosmological context, there is an absolute upper bound on what that correlation length can be. Okay, yeah, any is limited by causality to be smaller than the Hubble radius, the size of the particle horizon. L correlation. than the particle horizon at the time of the transition. Okay, so yeah, the particle horizon is sort of like the distance that light can travel since basically the beginning of the Big Bang until some later time t. So that's like the formal definition, and then this is of order, as you know, probably everyone here is familiar with this, of order the inverse Hubble rate, okay, the Hubble radius of the universe at that time. So this is just a very simple observation. So causality alone requires that the correlation length is bounded by basically the Hubble radius, and therefore this leads us to the natural expectation that we should expect at the very least one defect produced within a Hubble volume. Okay, so the number density of defects, typically will be of order 1 per correlation volume, and this has to be bounded by h to the minus 3. Okay, so one per Hubble volume at the very minimum. Surek did actually went back to this, and he actually showed that this is a severe lower bound. For example, in cases where the transition is first order, this can actually be a lot bigger than 1 per volume, but at the very least 1 per volume. So yeah, so let me illustrate how that may look like. So let's go back to the example of a C2 global symmetry. So we know, as T drops, phi develops a vacuum expectation value that has to be either plus V or minus V. But whether it's plus V or minus V is a choice that will be uncorrelated on different Hubble patches. Okay, so if we look at a snapshot of the universe at the time of this phase transition, so each of these guys would be sort of like a different Hubble patch. Let's say we're looking at different Hubble patches. So this could be some random choice. And then separating these choices of plus or minus vacua, we will have sort of domain walls. Okay, so this will lead to a network. Okay, let me get this right. So separating each of these guys with plus and minus, there will be some network of domain walls, which in this case, will look something like this. It will look something like this, okay? And the choices would be sort of like independently. So you're sort of left with like some network of domain walls in the universe that will look something like this, separating these various degenerate vacua. This is not here, obviously. Sorry. Okay, I think I got it right. Yeah, so natural outcome is not just one defect, but like you end up with some kind of network of defects, and this can be, I've illustrated here for the case of SC2 where these things are domain walls, but similarly you could do it for the case of cosmic strings where what would be uncorrelated across different patches would be like the orientation of the Higgs field on the plane. Okay, so the same thing happens. So yes, yeah. So at the time, let's say at the time of the phase transition, let's call it T critical. We might expect this thing to be. Sorry, this is plus. Yeah, so something, any number density of order Hubble cube. What happens later on? So how does this network evolve as the temperature further cools down and the universe expands? You can do something very naive, which is you know that for non-relativistic matter, the energy density in non-relativistic matter redshifts as a cube, like the scale factor of the universe. Okay, so as the universe expands, the distance between different point particles gets stretched in all three spatial directions. For relativistic particles, also known as radiation, we not only get the sort of like a spatial stretching, we also get the redshift of the whatever frequency of energy, right? So radiation redshifts as like 1/8 to the fourth. So we've gone from, so you can actually guess how a gas of cosmic strings or a gas of domain walls are going to redshift. For a gas of strings, as the universe expands, the strings only get pulled apart from each other in the two transverse directions. So this goes like a square. And for domain walls, there's only one way they can get away from each other. So this goes like 1/a. So the equation of a state of a gas of defects, whether they are cosmic strings or domain walls, is very different from the equation of a state of either matter or radiation, okay? And we do know very well what our universe is made of from precision measurements of the CMB, okay? We know we typically sort of parameterize the relative fraction of radiation, matter, and in particular cosmological constant in our universe by dividing, say, so let's say for radiation, we typically define these values of omega by comparing the energy density in radiation today to the critical energy density, that is 10 to the minus 5. For matter, we know that's something like on the order of 0.3, and I'm putting together like dark matter and baryonic matter. And then, of course, in our universe today, this is actually dominated by the CC, which is of order 0.7. Okay, so there is very little room in our universe for anything that has like exotic equations of state. We kind of know what's in it. I should say that this determination of like how a network of strings or walls behaves after being formed is actually a little bit naive. So if you had a non-interacting gas of strings or a non-interacting gas of domain walls, this could be true, and it's actually very easy to show. The reality is actually more complicated, and when people look at these systems in numerical simulations, it turns out that initially interactions between strings and walls are actually very important. And yes?
Why is it energetically favorable to make those big walls because they have some energy even at low temperatures?
It's not energetically favorable. Like if it was just the energetics of it, like you will never form domain walls. It's just like topology and causality just forces these things to form. Yeah. Even if energetically, it would be a lot better to just have like everything to be, one homogeneous vacuum. But there is just no way you can do that. If you want to satisfy causality and the fact that, topologically these things are like, stable independently. Yeah. Okay, so in reality, the way these things evolve is actually not as simple as what I've written there. And basically, numerical simulations show that in the shortly after the formation of these defects, the interactions between strings and also interactions between walls are important. So strings crossing a string will form a string loop. So this decreases somewhat the energy density in the network in a way that is not that simple. So I'm definitely not an expert in any of that, but let me just, the upshot is that the way it evolves would have an effective equation of a state that is still very different from matter or radiation. So qualitatively, that's still the case. So after formation, typically what happens is that these systems reach what is called a scaling regime, where in fact what happens is that the total number density of these guys remains of order Hubble cube. So this is to say that you still get basically one defect per Hubble volume, even at later times, okay? So just one defect or like, if you had previously n defects, it would still be the same n number of defects per Hubble volume, sorry. Yeah, and what people see is that the typical size of the domain wall, like let me call it the typical sort of radius, is also further the Hubble radius, okay? And if you remember, h is always up to some coefficient that changes depending on what is dominating the energy density. This is always proportional to time. So that's kind of what we know, how these things evolve. The sort of the energy density then in domain walls will be given by the number density times quote unquote the mass of one of these guys. We've just said that number density stays as Hubble cube, and the mass, if you remember, this is just the tension of the domain wall, which is a mass cube, dimensions of mass cube, times the area, which is going to be of further 1 over Hubble square. So we end up with something of further sigma times Hubble, and Hubble is 1 over T. So we end up with an energy density in domain walls that dies off as 1 over T, okay, as the universe expands. By comparison, during a radiation-dominated universe, so the scale factor goes as square root T. So radiation is dying off as 1 over T squared, and matter is dying off as 1 over T to the 3/2, okay? Which is to say, these guys, so the energy density in domain walls is actually redshifting much lower than matter or radiation. In other words, if domain walls were formed, at some point they will dominate the total energy of the universe. And that will happen. So let's estimate the time at which that will happen. So this is sigma on T. And the total energy of the universe we can always write down as Hubble square and Planck square. And up to order 1 numbers, this is m Planck square over T square. Okay, so this goes. And then we're left with, is this right? Yeah, T times, let me write it as G Newton times sigma. Okay, and this becomes order 1 at a time of order 1 over G Newton times the tension of those domain walls. It's kind of, if I had told you to just write down some random guess for what the time scale would be, that's the only choice you could have made, because there are only 2 scales in this problem, which are the tension of the domain wall and the Planck scale. So that's kind of like what we would have expected. Yeah, so domain walls will become dominant at time scales of this order. So is that even consistent? So, is that possible? Like, is that consistent with observation? So I've told you that we actually know very well what the universe is made of from CMB precision cosmology. So let me estimate what the effect of having a single domain wall exists in our universe today. What will be the contribution of that one domain wall to our current energy density? So can we have one domain wall today? Okay, so we're sort of going to do the same thing. So if we had one domain wall around today, this omega factor would be the domain wall energy density divided by the critical energy density. The domain wall energy density today would be, again, its tension times times Hubble today. So that's just the same thing we did earlier, except Hubble now. And this is divided by the critical energy density today, okay? So obviously this thing better be very small. Let me just demand that at least it's not the dominant contribution to the total energy density, okay? Just kind of being generous. And for this to be the case, the typical energy scale of this domain wall, so since sigma has dimensions of mass cube, let me just take the 1/3 of this. This has to be smaller than critical energy density over Hubble to the 1/3. Okay, the critical energy density today, what is it? So our universe is CC dominated, right? And the CC scale is like an MeV. You should know that number. So if no other numbers, so the CC is of the order milli-electron volts, okay? And it dominates the energy density, so our energy density today is that, roughly. Okay. And the Hubble scale today is of order 10 to the minus 33 electron volts. So that comes out to be something along the lines of 10 MeV. Okay. So a single domain wall with an energy density, a tension that has a scale above 10 MeV will completely dominate the energy density in our universe today, which is completely ruled out for many reasons, okay? So notice, 10 MeV is an extremely low scale. This is way below, the electroweak scale, way below the scale of QCD confinement. So any exotic situations like, parity domain walls that are broken, that appear at a TeV scale, or anything that is happening exotically at, much higher temperatures, there is no way anything like that can remain in our universe today, okay? If anything like that kind of network of walls ever formed, it must have disappeared by now. The situation is actually more stringent than this because we also know, that to a very high accuracy, our universe is highly homogeneous and isotropic. But if you have something like a network of domain walls with energy densities localized in these very thin regions, that obviously introduces an inhomogeneity. And that would introduce some inhomogeneity in our universe where delta rho on rho is of this order. But unfortunately, this would also introduce temperature anisotropies in the CMB of the same order. And we know that those guys actually have to be smaller than 10 to the minus 5. So I was being extremely generous here by putting this to 1. This should really be 10 to the minus 5. And then you end up something of the order of like 0.1 MeV, okay? So numbers a little bit smaller, but it comes to say that, it's ruled out by a variety of considerations. So these things need to be got rid of. This statement that domain walls are basically inconsistent with our current cosmology is what goes by the name of the domain wall problem. And this was, I think, discussed for the first time already in the 70s by, Soldovich and collaborators. And it's basically, a problem in any theory that has a spontaneous breaking of discrete global symmetries that are otherwise exact symmetries. So obviously, the way to get around this problem is by the symmetry otherwise not being completely exact, okay? So if there is a small amount of breaking, maybe explicit breaking of that discrete symmetry, then that's a way around this problem, okay? So if instead of having, two vacua which are completely degenerate, maybe there's a small imbalance in vacuum energies between one vacuum and another vacuum, then this gradient, this energy gradient, will make one of the two vacua energetically preferred, okay? And what will happen is that, let's say, well, in this case, yeah, the plus vacuum is energetically preferred. Well, what that means is that the regions of which are in this sort of preferred plus vacuum will just grow bigger and bigger and eat all of the rest, all of the kind of like false vacuum eventually. So let me just sketch that and what that actually entails. So explicit breaking of a global symmetry can actually get around this problem. And it's a nice thing that it happens to be that explicit breaking of an otherwise global symmetry is sort of like a requirement in any UV-complete theory of quantum gravity. So let us estimate what kind of size of breaking we need just by considering Planck-Suppress, the leading Planck-Suppress operator. So initially, let's say consider a zero temperature potential like this with the degenerate vacua, and we add some small perturbation with some coefficient epsilon and Planck-Suppress, but otherwise this is a symmetry breaking operator, say 5 to the 5. So dimension 5 operator. This thing induces an imbalance in the energy densities of the two vacua, which is going to be of order epsilon b to the 5 over m Planck. Okay, which is much smaller than the overall scale of the potential b to the 4, provided v is not very close to m Planck and that epsilon is not large. So the way these kind of domain wall networks get kind of destroyed is because there are basically two competing forces now acting on the wall, okay? So there's one act that comes out of the fact that, so any domain wall, say Hubble patch, is not going to be a completely sort of otherwise straight domain wall. There will be some kind of curvature radius that, in the absence of any other structure, will be of order the Hubble radius. And say the force on the wall due to the tension per unit area, that's going to be of order the tension divided by the radius at the time, which is just to say, and the radius, let's say that radius is of order Hubble length, which is of order time. So this is going to be of order sigma over t. But if there is also some type of imbalance between the two vacua, there would also be a pressure for the sort of true vacuum to kind of expand against the false vacuum. So that leads to a force per unit area that is precisely this difference in energy density. So what you see here is that if this guy is really tiny, initially the network evolves as if this wasn't there, okay? The string tension just wants to stretch the domain wall to basically fill the entire Hubble patch. But the effect of this force becomes weaker and weaker as time goes forward. And at some point, it will get taken over by the difference in energy density. So the whole thing will just collapse at a time when the two forces are basically comparable to each other. So collapse time scale is something on the order of sigma over delta v. Which also, if I had asked you to kind of just randomly make a guess for what the time scale would be, that's the only object with dimensions of time that you could have written. So now what we need is, so we want the time scale to be short compared to the time scale that it takes for the domain wall network to become dominant, okay? So we need that collapsed time scale to be smaller than the time at which these guys would dominate the energy density of the universe, which is g Newton sigma. Okay? So that, interestingly, this puts a lower bound on how much a symmetry has to be broken for this to work out. So delta V has to be larger than g Newton sigma square. So sigma square and Planck square. So if we have a particular sort of origin for this explicit breaking, something like epsilon b to the 5 over m Planck, this will give us a lower bound on how small that coefficient, that symmetry breaking coefficient has to be for this model to be consistent with cosmological constraints. Okay. Okay, any questions up to now? So what I want to do kind of in the last half hour is, so what happens when this network of domain walls collapses, and actually similar statements are true for a network of strings, is, well, one of the things that happens is that gravitational waves are produced in that process. So one of the things I want to do in this last half hour is to estimate what the typical frequency and the typical strength of the background of gravitational waves would be. There is another source of gravitational waves that is actually very similar to the domain walls, to the gravitational waves produced by a network of domain walls. So in the interest of doing things once nor twice, let me sort of mention that first, and then we will do a single estimate that is going to give us the answer for these two various cases that are both of them kind of some of the main contenders for production of gravitational wave stochastic backgrounds, and that has to do with whether the phase transition in which, for instance, these defects were formed, although it could also be a phase transition in which defects are not formed, so it's also like a little bit more general. But it has to do with whether that phase transition is first order or second order. Okay, so let me just remind you briefly what that means. So this is a huge oversimplification, but so oversimplifying by like a huge amount, there are like two ways a phase transition can take place. Okay, one case is if, say, at some very high temperature, the effective potential looks like this. So this is much bigger than, the critical temperature of the transition, however you want to define it. At zero temperature, maybe we have like the typical zero temperature potential we've been considering. And if you go from here to here, sort of in some smooth way, in which this high temperature minimum sort of smoothly becomes a maximum, and then the true vacuum appears. So the field is sort of like homogeneously varying as the temperature drops. This is what we call a second order phase transition. So in particular, heat capacity is varying continuously. The other sort of opposite possibility is if getting from here to here actually happens through the coexistence during some time of like two vacua. Okay, so at some point a second minimum of the potential appears. that second minimum at some point becomes sort of deeper than the high temperature minimum. And then once the probability of once it is sufficiently energetically preferable, this transition will proceed not homogeneously in equilibrium, but it will proceed via nucleation of bubbles of the new phase, okay, of the new preferred minimum. And this is a highly in-equilibrium process. And as you know, so this is T drops. Okay, so this is just the cartoon picture of what we mean when we say a first-order phase transition. Okay, I got rid of it. It turns out that, okay, I shouldn't have deleted that. So in our expansion of the finite energy density for when we were sort of expanding the effective potential, I was telling you that bosons can contribute to that effective potential with this kind of non-analytic cubic term, okay? Not fermions, but bosons will have this cubic term. It turns out that this type of appearance of a second minimum can be there whenever there is a cubic term in the effective potential for the field in question. Okay, so if theories where the effective potential at finite temperature feature like a strong cubic term, those are situations where a first-order phase transition can happen. Okay, there are a lot of things that I wanted to say that I'm not going to have time for, but let me just think. Before we estimate gravitational wave background, let me say two things that I feel like are important for kind of general culture purposes. So one is that if you were to compute the size of this cubic term in the standard model, so this is also typically some of the couplings involved between the Higgs and various other particles. And if you were to plot what that finite temperature effective potential is for various temperatures, you would actually find the picture very much like this, okay? And you would conclude that actually the electroweak phase transition in the standard model is first order. That's amazing. And we're going to see gravitational waves at the weak scale. And that would have been wrong, okay? And that is wrong because at finite temperature, using perturbation theory, which is effectively what we've been doing here, when I told you this is the leading contribution to the effective potential, I was assuming that the only effect I was sort of considering was the dependence of the masses of the various particles on the field phi, okay? But I was not including like additional interactions between the various fields. So in some sense, it's sort of like diagrammatically, it's sort of like a one loop effective potential approximation. But you could say, well, actually, like in the standard model, the couplings are perturbative, and we do perturbative calculations for the LHC, and actually they seem to be giving us the right answer. So why is it not working here? The reason is that at finite temperature, perturbation theory requires more than just small couplings, okay? Okay, and the reason is that so the Bose-Einstein distribution function, distribution for bosons, is given by, as you know, is e to the omega on t minus 1. So at small energies, or if you want sort of like at high temperature, this thing grows like P over omega. So this is for omega small. Okay, in other words, this leads to at finite temperature. So the fact that the occupation numbers of bosons are growing a lot, sort of in the infrared in terms of energies, are growing linearly. This means that interactions are actually enhanced at finite temperatures for low momenta. So yeah, if we're dealing with particles with mass and momenta that are well below temperature, the large occupation numbers that you can have in a Bose-Einstein condensate completely wrecks your ability to do perturbation theory. Okay, and then the only thing you can do is actually put the system in the lattice, and from the lattice we know that. So we need lattice, and from the lattice we actually know that the electroweak phase transition in the standard model is actually not even a phase transition. It's what goes by the name of a crossover, which is actually kind of a more smooth, continuously varying version of a second order phase transition. So a very sort of like equilibrium thing. And just for completeness, let me comment on what happens with the other phase transition that we know also happens in the standard model, which is the deconfinement transition of QCD. So yeah, this is something that happens. So this is something that happens at temperatures of order the QCD scale, okay? And we also need lattice, obviously. And from the lattice, we find the following thing. So, I mean, some of you may actually have seen this plot. So from the lattice, this is actually a question that depends very much on, so if you just look at kind of the phase diagram for SU3 gauge theory, the answer actually depends a lot on how many light quark flavors there are, okay? So let's see. So let's assume the mass of the up and down quarks are the same, and we can vary them sort of from 0 to infinity, and here we have a third quark. So this line here, where like the mass of these two guys goes to infinity, this will correspond to the one flavor case. This other horizontal line here, where the mass of the MS, this mass is infinite, this will be the two flavor case. And then this diagonal line here, where everyone is massive, well, but not infinitely massive, that would be like the three flavor kind of line. So it turns out that, so in this phase diagram, there is a region here where, in particular, including this point here, with no light flavor, so this could be pure gauge. Here, the transition is first order. There's also another corner here with three extremely light flavors, where the transition is also first order. And the physical point sort of corresponding to the standard model is somewhere here, okay? Where the transition is, again, also a crossover. So something like extremely sort of equilibrium, temperature. Okay, so this is kind of just for general culture purposes, so that you know what happens in the standard model. But beyond the standard model, a phase transition in the early universe that is first order is actually something that happens very commonly, both within minimal extensions of the standard model, but also more generally in theories with aerodynamics. So for example, a classic example of theories where the electroweak phase transition actually becomes first orders are theories that try to explain dynamically the baryonase symmetry that we have in our universe. So you may remember from your some undergrad course that generating a baryonase symmetry requires like the three Sakharov conditions, one of which is a strong deviation from equilibrium at some point in the early universe, and a first-order phase transition can be exactly that deviation from equilibrium you need, okay? And that can be built into the standard model by even just one extra scalar field that couples to the Higgs that can enhance this cubic term enough to produce, an honest-to-God phase transition at the electroweak scale. So let me now go on to make the estimate of what a gravitational wave signature for that would be. And the dynamics of a first-order phase transition, in particular, as far as the production of gravitational waves are concerned, is actually very similar to what happens in the collapse of a network of domain walls, okay? So yeah, so just as a reminder, for a first-order phase transition, what happens is we start in some, let's say we start in some homogeneous vacuum where the symmetry is restored, so the bev of phi is 0. And eventually, it will become energetically favorable to nucleate bubbles inside of which the symmetry is now spontaneously broken, okay? So there will be a few of these per Hubble patch. The energy density inside these bubbles is smaller than the energy density outside. So there is an outward pressure that wants these guys to expand. And the way the transition completes is when these guys grow large enough that they meet each other, and eventually the entire universe just becomes a new homogeneous true vacuum, okay? And it is in that process of collisions of bubble walls that gravitational waves are produced. So collisions of bubble walls. And very similarly, so when we sort of introduce this energy imbalance between the two vacua on either side of the domain wall, that outward pressure was what allowed us to sort of get rid of the entire network of domain wall. So that ends up also being sort of a collision of domain wall. So these two things are, as far as the gravitational wave production is concerned, there are some differences, but roughly speaking, the two things are very similar. So we're just gonna do the estimate that is gonna be good for either of them. So there are two things that characterize. Well, I should say something first, which is, these gravitational waves are not like the gravitational wave signatures we get from LIGO, right? Like LIGO, we see, this one event that has, a specific monochromatic frequency that we can actually even localize in the sky in some cases. This is not like that. This is happening so early in the history of the universe that, imagine there are an order one number of collisions happening early on in the universe, but if you compare the Hubble volume, if you compare the Hubble volume at the time this transition is taking place to the Hubble volume today, this is a tiny, tiny, tiny number, okay? Which is the same as saying that today, the gravitational waves produced very early on, they would arrive to us as if they were coming from all possible directions randomly. So what that means is that you don't get a monochromatic signal. You actually get something that looks like a stochastic background of gravitational waves. So something like the CMB but just made of gravitons. Okay, so there are two things that we want to sort of estimate as far as these gravitational waves is concerned. One is the typical frequency that that gravitational radiation will have, but also how strong the signal is. So the characteristic frequency. So at the time this process is taking place, both in this case and for the domain walls, there is actually only one length scale that is relevant, which is the curvature radius of these guys at the time this is happening. Okay. Now, that's happening very early on. We're observing these gravitational waves today, and we want to know what the frequency is today. So we're gonna get an additional redshift factor just from the fact that the universe has been expanding since then. This radius, typically, I'm going to parameterize it as a fraction x of the Hubble radius at the time of the transition, and I'm going to be, cavalier with like factors of G star and just approximate this redshift factor by the ratio of temperatures now and back then. So this is something like, there is this factor x over Hubble, and then T naught over T. But, let's say this is happening when Hubble is a radiation-dominated universe, then Hubble is just roughly T squared on a Planck. Sorry, this is... this is multiplying, actually. This is H times Hubble, T squared on a Planck. So the frequency we would observe today is just, up to this numerical factor would be set by the temperature at which this happened, and then, with some multiplying by T naught over n Planck. So let's say, let's normalize this to temperatures for the electroweak scale, and let me say. Yeah, this is also x to the minus 1. Sorry. Let's say the size of the bubbles at the time of collision is for their, say, 1% of the Hubble radius. And let's normalize this to like 10 to the 2 GeV, which is the scale relevant for the electroweak scale. So the numbers here come out to be for their 1 millihertz. Okay. So this x to be order 0.01. I've chosen this in particular because, in thermal first transitions, where people look at these systems numerically, this is typically the size of the bubbles at collision that they observe. If you wanted to do this estimate for a domain wall, you would want this thing to be more like order 1. In which case, this frequency would be a little bit lower, 10 to the minus 5 hertz. But notice in particular that 10 to the sort of millihertz frequencies is exactly the frequency where the upcoming LISA detector is going to be the most sensitive. Yes?
Sorry, just what's the exponent?
10 to the 2. Yeah, so this is just the weak scale. So 100 GeV. Yeah, so this is exactly the frequency range where the upcoming LISA experiment will be most sensitive to gravitational waves. So, and indeed, one of the science missions of LISA will be to probe the nature of the electroweak phase transition. In order to make that claim, though, we need to have an estimate also of how strong the signature is going to be. And this is the last thing we're going to do. So yeah, the one parameter we've already dealt with is the frequency. We also care about the strength. So, assuming everyone here is done a course in GR, you might remember that the power in gravitational waves is given by the quadruple formula. Okay, so power is G Newton, and then there's some averaging of like 3 time derivatives of the quadruple moment of whatever system you're dealing with. I assume this at least looks vaguely familiar. Maybe. Yeah, so quadruple moment is just the second moment in the energy density. So very roughly, for any system, this is basically just mass of the system times the typical size of the system, okay? Very roughly. So, yeah, so for one of these bubble walls, they are nucleated with some radius at finite velocity, but so as the bubbles expand, they actually very quickly start moving with relativistic speeds, and you can estimate sort of like the surface, like the amount of energy in the surface of this moving wall, which is going to be for the area times the tension of that wall, but you get an extra enhancement by the gamma factor if it's moving relativistically, okay? This energy needs to come from somewhere, and the place where it's coming from, so this could be sort of like the mass of, so this is what we will call like effectively the mass of this object, right? This energy needs to be coming from somewhere, and that somewhere is the fact that as this guy gets bigger and bigger, you're winning energy by the vacuum here being at less energy than the vacuum outside, okay? So just by energy conservation, we know this is going to be further, this volume times that difference in energy densities inside and outside of the bubble wall. So, right, so ignoring factors of pi, we know that the mass is basically r cubed times this delta V, and then the overall size of this system at the relevant time, which is when these things are colliding, is for the radius square. If I'm sort of like, Cavalier, and I just say, well, let's say this is a further Hubble size, or at least proportional to Hubble size, and this goes like the time, I got something that goes like delta V t to the 5. So now, let me go back here. So yeah, we got, up to, or the one number, some quadruple moment that is like delta V t to the 5. If we take 3 derivatives, that's going to be roughly delta V t squared. So power in gravitational waves emitted would be something like G Newton delta V squared t to the 4th. Is that right? Yes. Now, total energy, right, is integral of the power over the time the transition is taking place. So let's say that's also for the Hubble time. So so we end up with something for the G Newton delta V squared t to the 5. Okay, and the energy density in gravitational waves produced, and this will be at the time they are produced, is just going to be this energy we've just calculated, t to the 5, divided by the Hubble volume at the time. But Hubble volume is just t cubed. Okay, so this is just going to be G Newton delta V t squared. If we were a little bit more careful, we could see that actually, rather than t squared itself, this is just delta t, which is to say how long the transition takes. So basically how long the source of gravitational waves is on for. So that's the energy density in gravitational waves, up to factors of order 1 that will be produced in a first order phase transition, but also the same thing is true if that delta V is the difference in energy densities at either side of the domain wall network. So now all we have to do is compare, we have to do is redshift the energy density to today energies, and then compare it to the critical energy density. And then we're done. 5, okay. Yeah, okay, so I'll just do this and we'll finish there. Yeah, okay, so we want to compute what omega gravitational waves is today, which is that gravitational wave density redshifted to today over the critical energy density. So that redshift factor is just going to be, to leave in order just the ratio of temperatures. And okay, you can plug all of this here, and I'm just gonna write down what the number is. So that comes out as 10 to the minus 5. And I am normalizing this in a way where this delta V is measured relative to the total energy density at the time of the phase transition. And I'm also normalizing this to a duration of the phase transition of order the Hubble radius. In the literature, sometimes these parameters goes by alpha and inverse beta. So parameters that they are sort of telling you about the strength of the phase transition, the latent heat that is emitted, and like how long the phase transition goes on for. Now, 10 to the minus 5, notice that if you're actually a little bit more careful, this comes out to be 10 to the minus 5, not 10 to the minus 4. This is already at the level of what is ruled out, actually not by gravitational wave experiments, but again by the CMB. So a stochastic background of gravitational waves also contributes to the total energy density in our universe today, and we know that raw radiation is of order 10 to the minus 5. So any additional contribution to our energy density has to be not bigger, at least, than 10 to the minus 5, okay? LISA will be able to, will be sensitive to stochastic backgrounds of gravitational waves all the way down to 10 to the minus 12 for the relevant range of frequencies. So let me just draw one more thing, which is, so in the next few decades, obviously everyone has heard about LIGO. So LIGO operates between 1 hertz and sort of 10 to the 3 hertz. LISA will operate somewhere between 10 to the minus 5 and 10 to the minus 1 hertz. And then at very low frequencies, another very interesting types of experiments are the pulsar timing arrays, okay, that operate between sort of 10 to the minus 9 and sort of 10 to the minus 7, 10 to the minus 7 hertz. These have, different sensitivities to, the strength of a stochastic background they could discover. LIGO, it's only sensitive to omegas of order 10 to the minus 5, 10 to the minus 6. So if you're extremely lucky and there was some spectacular phase transition in the universe, LIGO might see it at these frequencies, but it doesn't really go far enough in energy densities. And then, here in this region, so experiments like NanoGrab, also the European pulsar timing array, these are sensitive in this frequency range to omegas of order 10 to the minus 9, okay, which are decent, respectable sensitivities. And so yeah, so for the next few decades, we'll see what this thing has to tell us. I mentioned that in the standard model, both the electroweak phase transition and the QCD phase transition are not first order. They are very, smooth equilibrium processes. I also told you yesterday the standard model contains no topological defects. This means, in particular, that within the standard model itself, there is actually no way to produce a stochastic background of primordial gravitational waves. Okay, so any stochastic background of gravitational waves that has primordial origin, that will be a clear smoking gun for dynamics in the early universe beyond the standard model. One caveat is that, of course, there can be astrophysics sources of stochastic gravitational waves, and one will have to deal with those to see, to what extent, you actually have something primordial. But anyway, I hope I convinced you that, it's a very exciting time to be thinking about, implications of formal theory for particle physics, phenomenology, and that there are tons of, interesting experiments in the next few decades that hopefully will tell us something very interesting about, what's beyond the standard model. Okay, that's it.
Maybe, given the time, maybe just one question, if there are any. We may be ready for a weekend rest.
Yeah.
All right, well, this was the last lecture for Isabel. Let's thank her one more time for her great lecture series. I hope everyone has a restful weekend. I remember when I reached this point in TASI, it was just starting to get a little stretched. You know, you've been here a while, so have a relaxing time, have a good time. We'll see you Monday morning.
Okay. Thanks.